И какой-то пульт есть, наверное, внешне, да? Или надо...
Можно мышкой, можно... Да, сейчас.
Надо щелкнуть на презентацию, сделать режим просмотра.
Полный экран.
Shift. Какой-то вот 5, по-моему, видишь. Или просто икон.
Сейчас. Может, у нас не тяжело.
То мы тогда сейчас...
Да.
Есть вперед-назад, есть. Есть.
А в зуме все видно?
Поинтер тут есть какой-то? Не видно, да? Поинтера нет.
Поинтер есть, но его...
На этом
На этом вот так. Хорошо.
Поэтому, может быть, проще...
Да, рукой. Ну, я рукой буду. Зарядом буду. Все отлично. Такая домашняя обстановка.
Но нас сегодня вот должны наши все адвайзеры тоже слушать. Миша Портной всегда значит, сейчас посмотрим. То есть тут у вас будет большая еще онлайн аудитория. Сейчас они все потихоньку присоединятся.
Все, еще теперь.
Ну, и я начну быстренько вас представлять, потому что времени очень много. So, ladies and gentlemen, today we have a great honor hosting Professor Vladimir Pudalov from Lebedev Institute, Academician of Russian Academy of Science, and very, very well known, internationally famous condensed matter physicist who worked in many countries, in the US and Canada, and currently is at the Ginsburg Center in Lebedev Institute. So he will tell us something about unusual effects in transport and magnetism in layered antiferromagnetic semimetals. So please manage yourself. Let's start.
Good morning to everyone. I think I was told that I have to speak in English, right? Okay. I forgot to write here that I'm also chair of the MIPT at Landau School. So basically the experiments are done in this beautiful building, which is called after Ginsburg. And this is the outline of my talk. I will present some overview of the stoichiometric pure, I mean, without any dopants, non-Weyl semimetals. And some of them are superconducting, and other seems to be just topologically trivial, but exhibit a number of unusual properties. Some of them were initially studied by at Vasily Stolyarov laboratory, and we made further studies, and I will explain here the puzzles and the answers. So the prehistory was quite curious. We initially thought, maybe 5 years ago, we thought to make a series of compounds based on indium arsenide, because there were predicted to be some trivial, some non-trivial, some non-trivial topology, but my colleagues just mixed up and took took a box where it was written tin, but in indium, but in fact that was a tin. So we started with the tin arsenide, and we moved to tin for antimony 3, and finally quite interesting superconducting material, which I will talk briefly because this was a matter of 2024, and then we moved to magnetically ordered semimetals like this, and appeared to be quite interesting story. So all of them are layered and magnetically ordered at low temperatures. The magnetism comes from the inner shells of europium. These are 4 F cells, and in plane there is the largest exchange integral, and therefore in plane they are ferromagnetically ordered, but upon cooling, the interlayer exchange makes them antiferromagnetically ordered. Some of them, this is a kind of spiral antiferromagnetic states where the vector, the magnetic vector turns in some by pi, in some other by pi over 2, and so on. It doesn't matter at the moment. So these are layered materials where European magnetic layers alternate with the major part of my talk will be about either iron and arsenide or tin and arsenide layers, which these layers supply the electrons to the conduction band. All of them are conducting, and some superconducting. So the magnetism comes from europium, and mainly, and conduction comes from tin and arsenide or iron and arsenide electrons. So we started with the tin arsenide. It appears to be quite trivial. Type 1 superconductor we did. And this was just the beginning of the story. Then we started studying tin for arsenide 3. And this compound has a quite low critical temperature, about 1 Kelvin. Therefore, these measurements could not be done in both in Vasily laboratory and my laboratory. So these measurements of the scanning tunnel spectroscopy were done in by Peter Weyl, who had STM with the dilution fridge. And finally, we moved to more interesting materials which actually combines the properties of layered semimetals, but because it is stacked, it stacks two layered materials with different ion radius, like europium and rubidium. Therefore, it's internally strained, and with no doping, it becomes superconducting. So, and the problem, it's quite an old problem, is how the magnetic order interact with the superconducting pairing. In fact, the electrons propagate because freely propagate delocalized electrons in magnetically ordered, magnetically varying in space magnetic field. Moreover, as we initially thought, actually there is quite a puzzle because this one and the same electrons are participate in superconducting pairing, and also they help they promote magnetic ordering of the europium atoms because they are located quite far away at about 13 angstrom from each other, and therefore direct dipole magnetic order is ineffective. So we thought this is a puzzle. In fact, there is no puzzle. But we understood this 4 years later just by putting some numbers on the various kinds of interaction. But at the moment we decided to, at the beginning we decided to study this experimentally, and it was quite interesting. So usually superconductivity develops at temperatures much lower than magnetic ordering temperature, than Weyl temperature. But in this material, it happens just in opposite case. The superconductivity starts at the beginning, and then upon cooling, magnetic ordering sets. The pairing, as in all other iron-based pnictides, the pairing mechanism is believed, and probably this is the case, is due to fluctuations of the spin fluctuations, and this is a multi-component order parameter. So we have quite a complex picture of intralayer of ferromagnetic order, where europium atoms have a strong ferromagnetic order in intralayer, and interlayer antiferromagnetic structure. And I wish to stress that this is a stoichiometric material, therefore it makes very interesting and fruitful study of the materials with no doping effects, no impurities effects. So this is a picture, and this was done in Vasily laboratory, and since it consists of alternating rows of rubidium atoms and europium atoms. Rubidium is the largest atomic radius dipole. When you cleave it, for studying experimentally, you have to cleave materials for RPS and for STM, and this cleaves most often along the rubidium, and this is quite sad because you don't have a direct access to study superconductivity by STM. The tip doesn't come close to the superconducting layers. So again, this picture illustrates what I said. The largest exchange is in plane, and then the antiferromagnetic exchange interaction between various planes, and I will then tell how it is done. And theoretically, was predicted, calculated, and experimentally confirmed that the magnetic polarization rotates by pi/2 from layer to layer. This was experimental outcome from scattering by elastic scattering by polarized neutrons, and beyond the regular peaks located at expected distance, there are some satellites which die at the temperature of magnetic ordering. So there is some event that something should occur at 15 Kelvin, and this was immediately seen in experiment. When you study, say, AC susceptibility, you see some hump around this magnetic temperature. So there's definitely there is an effect of some weak effect of magnetic ordering. Of course, nothing can be seen on the on transport, on the drop of the resistance, and even on M over H. This is a DC magnetization. There could be noticed something in the vicinity of the magnetic ordering. But actually, we were puzzled because we expected that let me move to band structure. The band structure is actually usual for all other 122 superconductors because it consists of two cells of 122 type, which are usual iron-based superconductors. So it's just twice bigger lattice cell. In ARPS and in calculations, there are usual multi-band structure where inner electrons, inner walls, there are multiple coaxial cylinders, and some electron bands at the corner of the previous zone. On all these electrons, which form the superconducting pairs, that comes from these bands, and their multi-band nature promotes the S plus minus pairing by spin fluctuation. What about magnetic layers? The magnetic moments comes from iron 4f electrons, and their energy and their band is located much deeper at about minus 1.5, 1.6 eV. As I said, this was the experimentally. This was measured by ARPS. You can see here the very powerful band of 4f electrons of iron, and calculations, and also this can be noticed from scanning tunnel spectroscopy, where some dip in the vicinity of related by the density of states related to 4f band.
So
now,
may I ask, so do you have a topological phase transition when you change temperatures, go through
No.
15 Kelvin?
No, there is topologically what in that sense, it's topological trivial. There is no direct points or some other features in the vicinity of the Fermi energy. But this picture, it's quite an old picture of 2021, 2022, which shows how the superconductivity develops in ARPES measurements, because doing these measurements, you can notice where exactly the superconducting pairing occurs, and this can be seen here on the cross cut. At high temperature, the red curve it drops down because there is no, because the states above Fermi energy are empty, so this is natural. But below the superconductivity sets, the green curve shows that the excitation, the Bogoliubov particles moves there. And probably there is a picture, movie shows how the superconductivity develops upon cooling. You see that the electrons, the excitations relocate to above the gap. I want to move back. Okay. Okay. From ARPES measurement, so the question which we want to understand was how the magnetic ordering develops affect the superconductivity. So from these ARPES measurements, we did measurements of the superconducting gap, and there are three gaps were noticed in ARPES measurements, and they developed smoothly with no features exactly at the temperature of magnetic ordering. So by doing STS spectroscopy, we could obtain more information because, as I said, the tip doesn't come close to the superconducting layers. But another technique, Andreev reflection spectra, provides much more detailed information. Two gaps were seen here. I don't know why. Sometimes one can see three gaps, sometimes two. There was an example. Nevertheless, there is nothing specific at the temperature of magnetic order. So the superconductivity seems to be completely not affected by the ferromagnetic order. We, of course, said a number of trivial arguments in favor of the separation of the magnetism and superconductivity, saying that the magnetism and superconductivity are far away in energy. The superconducting layers and the magnetic layers are separated in the real space, and so on and so forth. But in fact, then we much later put some numbers, we understood that the antiferromagnetic ordering, which is not possible to make only due to dipole direct interaction of European atoms, it's mainly occurred due to super exchange interaction, not by RKY, but due to super exchange through the delocalized orbitals of iron and arsenide, and which are the most effective. So RKKY, by the way, is curiously, it has a opposite sign. It oscillates as a function of distance, but for this particular distance, it produces a weak ferromagnetic effect. So it is negligible on the background of the super exchange interaction. At this moment, it may be asked whether or not the antiferromagnetic order and superconductivity, by a number of reasons, completely independent. But in fact, it's not. And we have some evidence for this. We are doing measurements. And this picture shows that the density of superconducting condensate and NS, which is proportional to is related to the magnetic penetration depth and the critical current and critical field. The first critical field, it exhibits indeed some hump in the vicinity of the magnetic transition, so that the magnetic ordering does not affect the superconducting gap, but does affect the density of condensate. So these measurements are in progress, not published.
What kind of experiment do you use to detect this critical current?
We did constriction by focused ion beam. We just make a constriction on order of sub-micron constriction and apply microamps to get.
So it should be dependent current. It should
Yeah,
be dependent
current,
current. It's quite strange that there is some peculiarity in the dependent current, but still no any sign at the gap behavior. It's extremely strange. Yeah.
There was
Yes.
quite a serious theory on this issue by Koshelov and by
Mhm.
Pustin that predicted indeed that it should affect not the gap, but the superconducting density,
Mhm.
the pair density of pairs. Now, but we understood this much later. But at these times in 2021, 2022, we were puzzled how to understand this material. We decided to separate it in two blocks, which are maybe easier to study. As I wrote here, cartoon how we decided to proceed, and we started with the European semimetals like this, and we made a number of measurements. We thought that it may be very simple. You understand, based on these studies, we understand what is going on, and then we applied this knowledge to more based material. It didn't help. It didn't work in this way because we immediately saw a number of puzzles. The first puzzle is in transport. And actually, this is a more general behavior, which is intrinsic to a large variety of van der Waals type antiferromagnetically ordered materials. For example, this famous MMBT, and all these materials show negative magnetic resistance like this. It's not large, it's about, you see, a few %, and it develops exactly correlated patient with magnetization. But we didn't study this material because it's more complex, it's magnetic, it's not non-trivial, topologically non-trivial. And here I just show a number of topologically trivial materials, and all of them show the same parabolic negative magnetic resistance. You see here that it's general effect, and everywhere it range in the it's about in the range of 4 to 6%, and sometimes a little bit. It's a weak effect. Specifically for what we studied here for European team to arsenide 2, it develops exactly in a similar way, correlated with the magnetization. As you increase magnetic field, you saturate European ions, and immediately the negative magnetic resistance vanishes. And indeed, because there is this material is easy plane antiferromagnet, so you rotate. When you rotate magnetic field in plane, nothing changes, but when you turn it perpendicular to the plane, it's a little bit harder to magnetize, and there's a minor difference. But when you scale this data for magnetic resistance on the saturation field, which is a complete spin polarization field, then it exactly matches each other. So it's isotropic effect. The effect is isotropic. The magnetic resistance is isotropic. Then for about 8 months, we were fighting with referees who listed a number of common knowledge, which everyone should know from textbooks, and we explained the referees one by one that they are inapplicable. The famous effect is Pudalov hopping and ferromagnetic oxides. Of course, we don't have both oxides or polaronic type transport. Then even more famous is GMR in iron chromium superlattices, which produce exactly negative magnetic resistance, which is well tied to the magnetization. It's much stronger. It's maybe factor of 10, but it's strongly anisotropic. When you apply current across or in plane, then you can either excite this effect or dampen it. Also, colossal magnetic resistance in granular superconductors or in AFM insulators, exactly for the same reason that we don't have insulator, we have a semi-metal, this is inapplicable. Then electron-magnon scattering. When I told once the story by Zoom, Sasha Finkelstein, who attended and was involved in magnon scattering, he said immediately, okay, this is magnon scattering. But this is wrong, because the magnon scattering produces negative signs only for ferromagnets. For antiferromagnets, it gives a positive magnetic resistance. The reason is very simple. It originates either from suppression of magnetic spin fluctuations or enhances the fluctuation. Finally, quantum scattering, this is also inapplicable because there is we don't observe either minimum of resistivity or magnetic impurities. We don't have in our pure samples, which I said that it's usually experimentalists deal with the ppm level of purity, but the effect is observed everywhere. Now, this was due to, again, to show that we don't have an axial insulator, which was put forward in some papers which tried to explain this phenomena. We rotate here magnetic field relative to the current, and we don't see any signatures of anisotropy, strong anisotropy that should be intrinsic to axial insulator. As I said, it is isotropic with respect to either current direction or field direction or whatever you think. It's isotropic effect. Now, when it terminates, then it transforms to parabolic rise, and this is a trivial effect because it's omega tau squared, which would this be single band material, the magnetic resistance will be zero, but in fact, as we see this omega tau squared, it's experimental proof that we have a multi-band material. This is a whole semi-metal with at least two groups of electrons and holes. And when so this is not a puzzle, we take measurements of the hole resistivity and diagonal magnetic resistivity, so we extract mobilities and scattering time, so we put this in textbook formula, and with no fitting parameters you apply, you get a nice agreement with what you see here. So above field saturation, above the spin saturation field, there is no puzzles. Now, the mechanism which the Pasha Grigoriev suggested is very simple. It is based on the fact that this is just a medical fact that you increase magnetic field, and the electrons which have a different spins relative to the europium atoms, they concentrate they concentrate closer to the plane of europium, which they prefer. And this is shown here in some units I will explain later. As you increase magnetic field, the electrons with a given spin, they redistribute from this to this band in real space. And this is shown also by result of DFT calculation that shows that electrons with certain spins are located closer to either this or this layer. It has a very simple effect, because even in the Born approximation, when you step back just to say that experimentally we see that this is a very isotropic phenomenon. If this is isotropic, then it immediately prompts us to consider point-like scattering. Just a common sense argument. Then we open textbooks and write down Born approximation for the scattering. The Hamiltonian can be written. It's 4 by 4, then it breaks into 2 by 2, and then you get eigenfunctions which depend on the certain factors, where the band splitting, since the electron wave function separate, that they immediately should be separated also in energy. And this splitting is mainly caused by exchange interaction. The spin orbit interaction much weaker. The Zeeman interaction is much weaker. It's an order of micro EV, and this is an order of 30 MeV. Okay, so we have a certain dependence where T naught is a transfer integral between across the layers, and this is the exchange splitting of inside the layers. And the only parameter that from the theoretical point rules this effect is the ratio of the exchange splitting to transfer integral. A few more formulas. Where the magnetic field dependence comes from. It's not, of course, from T naught, which is great, which is a very large quantity, but exchange splitting does depend on magnetic field. When you fully polarize the system, when you fully polarize the magnetic field, it vanishes. And it can be written here even from thermodynamic type arguments like this, and and finally you get a ratio of the magnetoresistance, which gives you parabolic dependence, and the prefactor is the ratio of what I said, exchange splitting to transfer integral. So depending on the ratio in various materials, you can get it smaller or later. For our case, according to experiment, in our materials, it's about the amplitude of the effect is about 5 to 6%, so we allocated somewhere here. But it can be greater or smaller depending on the band structure, on the exchange splitting in the band structure. And they did in DFT calculations done by Nikita Pudalov and Vladimir for our material. There is a exchange splitting an order of 30 MeV, but you understand that the exchange splitting is very complicated phenomenon because there are a number of bands and you have to average somehow. This is a very just a qualitative characteristics. For example, this to illustrate what I said for two different. There are two layers in between European layers. There are two different tin arsenide layers, and for one tin and for other tin, there are different, a little bit different band structure. But very well.
Sorry, I missed. So the magnetic moments are parallel to the layers, well, with a certain rotation in between the layers. Yeah, it says antiferromagnet by pi. Yeah, okay. But now you apply magnetic field perpendicular to the layers parallel.
In any direction.
In any case,
In any direction.
you see something like this.
Well, the simplest way is to apply in parallel. But when we apply perpendicular, we also rotate the magnetic moments of European and then finally tilt toward the field.
So you argue, in fact, that applying magnetic field, you have some angle for magnetic moments, and because of that, the exchange.
We feel the exchange.
You feel the exchange energy. Yeah, that's it. Yeah, okay.
Perpendicular. Now, everywhere, roughly, it has an order of 30 MeV, but you understand that this is only a qualitative estimate. What about T naught? So we have this almost definite. What about T naught? T naught is very hard to calculate numerically, but we have some prompts from the experiments. First, we have an anisotropy of the anisotropy of the resistivity, which is a factor of 100. Across the layers in plane, this very layered material, van der Waals material, so it's well conducting in planes and 100 times less conductivity across the layers. And the bandwidth of the conduction bandwidth. So from this to the bandwidth is huge, and we immediately obtained and estimate for T naught transfer integral, which is 410 MeV. From these two numbers, we can get 30 by 84, so it's an order of 0.4, while experimentally we have 0.23.
But resistance you measure in the plane, not perpendicular.
Both. In
Both.
plane or perpendicular, we scale it by the spin saturation field, and it becomes beautifully isotropic. Now we have more or less consistent estimation of this mechanism. We apply this to explain our effect, and we conclude that the negative magnetic resistance originates from exchange splitting, not from other known mechanisms, and it's isotropic. It's experimental proof. It's universal for 2D material compounds, and it can be greater or smaller depending on the exchange splitting. And again, I stress that the spin orbit interaction much weaker. Just G mu B is an order of microvolts, or sub-millivolts, and here 30 millivolts. And of course, we conclude that the puzzle is solved, at least to the first approximation. Now, the next puzzle is as follows. These nice, pure antiferromagnetic materials, ferromagnetic compounds, which have well characterized by X-ray, crystal lattice, and so on and so forth, they always exhibit some signatures of ferromagnetism, residual ferromagnetism. For example, and it's sample dependent. For example, if you take measurements of the magnetic susceptibility, you see that below the magnetic transition temperature, it should stay constant in one direction and drop down to zero in another direction. Instead, it diverges. And this is in a paper where authors specifically studied how to grow the sample with the best quality, with the highest quality in order to avoid this. All of the experimental studies exhibit signatures like this, and even some exhibit signatures of very weak hysteresis in DC magnetization curve, which of course is not intrinsic to antiferromagnetic studies. The problem that we deal with some ferromagnetic signs of some ferromagnetism in our sample, and people said, okay, there might be impurities. But if you put some numbers, you immediately conclude that it's unrealistic for the highest purity materials. Now, to explore this effect, we have taken, from the point of view of what I said, the worst sample, where these ferromagnetic type signatures are the largest. So we have a large number of samples, so we have selected some, and indeed, it shows magnetization curve like this with a well-pronounced non-linearity in the vicinity of the zero field. So we zoom this non-linearity and see the hysteresis effect. And all characteristics of this hysteresis, like the magnitude and the waves, they drop down to the temperature of antiferromagnetic ordering. So that already prompts that this ferromagnetism is just born by the antiferromagnetic ordering. So the two phenomena are very closely related. These also signature are enormously large here when we take measurements of the susceptibility. But by the way, I forgot to say that when people in various papers report this ferromagnetic ordering, they try to, to close eye on this effect by applying magnetic field, and then these ferromagnetic signatures are simply washed out. For this picture explains how magnetic field of 0.2 Tesla already killed this ferromagnetic type order. This is, by the way.
May I ask, but if there is some ferromagnetism, then potentially we can have this FFLO phase, yes, full differential. Right? Because
How this can be noticed?
or two
It's
spins
simply but I don't know how this can be noted. we don't have any signature of supermetals stain. Maybe by taking magnetic, or I consider if you have a local magnetic probe like NV center probe or street magnetometer, you scan and maybe find some like that. But we have not been done yet.
In the behavior of the gap, this full ferro-Larkin states could appear in the behavior of the gap, but you do not see any peculiarities of the
I
gap.
want to say that this is not superconductor. This is a simple trivial semimetal.
Then
Okay.
Maybe this will be some interesting, but okay. Now instead, we have taken transmission electron microscopy, and you see here, this is not just artificially drawn, this is a result from measurement. There is something going on in this line. And this line this is about 1 to 2% of this line per volume. And when you zoom, what is going on here, you find that there are some planar defects, like that one is enclosed by being rectangle, and they are missing thin layers. Instead, there can be seen an additional European layer, and the distance is smaller by 20%. And this is a nanometer width layer. It extends by several hundreds micron across. By applying on the power technique of analysis, we analyze what is going on here, and this is indeed very suppressed row of europium, missing rows of tin, and also we did measurements of what is going to be the electrons in europium. Europium has nothing specific; it's a normal state, but tin changes the valence. The tin is a quite curious material. Sometimes it has a valence of 2 plus, and here in this case it has a 4 plus valence. It's known, and then we turn to the entropy phase diagram on this triangle and find that close to what we study, europium tin to arsenide 2, there is another compound which is europium tin arsenide 2 due to valence 4 plus of tin. Then, and this compound is known. It is known that it has a cubic lattice, while our material has a rhomboedral lattice. And you know, to match the cubic with rhomboedral is not an easy task. And using all power of machinery, crystallographers, my colleagues, they managed to fit this. And it turns out that the minimal transition supercell layer consists of 35 atoms. And it slowly rotates from, slowly changes from regular to defect layer. And it has a general composition of all this, europium 7, tin 12, and arsenide 14. What is important? That the number of europium atoms is odd. Since it's odd, it must be ferromagnetic. It cannot be antiferromagnetic. So we immediately on this chemical analysis already obtained that the origin of the ferromagnetism comes from defect. And this is confirmed by DFT calculations. Nikita Pavlov did these calculations and found how the energy levels changes in recalculated then structure for this supercell for transition layer. But experimentally, we also were able to scan element to do the nanoscale elemental analysis for europium, for tin, for arsenide, and this confirms what I showed in the previous picture, that tin is almost vanishing in the defect layer. Now, from this measurements, I can make conclusion that the ferromagnetic features in van der Waals compounds originate not from impurities, but from defects. from neutral defects, and these planar defects are inherent in layered compounds because of the enthalpy of the regular compound, and defect compound is very close. You grow the sample at 600 Kelvin or maybe 1000 Kelvin, so the density of defect is so the defect can be naturally emerge at this temperature, elevated temperature. Okay, the defect cell, super cell contains an even number, odd number of uranium atoms, and therefore give birth to the ferromagnetism. Let me move to the last puzzle of my story, which is electron spin resonance. Again, these measurements were started in at MIT by Igor Golovchansky and Vasily Stolarov, and they started the same crystals, which are supposed to be trivial, topologically trivial semimetals with simple van der Waals bonding, interlayer bonding, and antiferromagnetic simplest antiferromagnetic easy planar action. Instead of what is anticipated, they saw the splitting of the electron spin resonance. It's supposed to be a single line, but instead Igor observed two lines, which develops. These measurements were done in broadband spectrometer, so he tuned the frequency from 5 gigacycles to 25, and he observed the development of the resonance here. The one line can be identified immediately. This is a normal acoustic mode of antiferromagnetic resonance. Another, the high frequency line was mysterious and was not identified, so Igor concluded that this might be ferromagnetic impurities. But again, we already suspect that this is not impurities, but the defects. And the only thing which Igor concluded that it doesn't have anything common with the optic antiferromagnetic resonance. What's important also that the amplitude of this line vanishes exactly at the temperature of magnetic ordering. So again, it originates from the same antiferromagnetic ordering. So having known already a story about defects, we modeled the sample with a two-phase metamaterial where the European layers here, the magnetic moments are drawn here by red arrows, and in between there are some planar defects with magnetic. We don't know where the magnetization is directed, but just for simplicity, I directed them either perpendicular in this direction or opposite direction, and some, if they are large enough, may have a downline structure like that one. So we have a model, and we apply this model of metamaterial, two-phase metamaterial. I assume that this the subsystem of the defects and the subsystem of the Hawkes lattice don't interact, they are independent, but in fact this is very naive approximation. Nevertheless, for the regular AFM acoustic resonance, we have a known dependence. It was used already before, and there is no fitting parameters because everything that comes here, the effective magnetization of antiferromagnetic magnetization and exchange field, they can be immediately found from DC magnetization curve and determined in an experiment like this. Now, having no fitting parameter, we immediately fit the frequency of the frequency versus magnetic field dependent that was measured by Igor Golovchansky, but this is actually already has been done by him. So far, there is nothing new, and we move further. We move further and think about a ferromagnetic resonance related with the defect, with planar defect. The ferromagnetic resonance frequency we can borrow from either Kittel book or Ashcraft's book, and like that. So just selecting a reasonable solution of this quadratic equation. We try to fit the experimental data of this M line, but for this we need certain parameters, which is not easy to take from measurements. We know here the magnetization is magnetization of the D field. It's not easy to obtain. From magnetization measurements of the hysteresis measurements I showed, we can only estimate it, and estimate it to be an order of magnitude smaller than antiferromagnetic magnetization. But here we use it as a fitting parameter and obtain 0.13, which reasonably fit is number of 10 diminishing. Now with this single fitting parameter, we obtain quite a reasonable fit of the experimental data. So being encouraged with this success, we repeated the measurements with the more sensitive technique. It's a cavity spectrometer with a fixed resonance frequency but varying temperature. And again, we see here the splitting of the resonance line, and we explore this depends as a function of temperature, not magnetic field, but temperature. And again, we see everything here develops as a textbook. The black rectangles are reproduced from what Igor did measurements, and blue and red are the new measurements. So this low resonance field or high frequency resonance are this M line, which we try to interpret as a ferromagnetic resonance. And its intensity again drops down to the temperature of antiferromagnetic ordering. Now this is a task, and we apply some quite simple formulas. For the temperature depends on the effective magnetic, for the antiferromagnetic resonance, we use the blue electron, which is reasonable, and it gives us temperature depends on the acoustic AFM resonance. And as regarding to the ferromagnetic resonance, we can either take the first order expansion of the vicinity of the critical temperature, this is just from thermodynamic, or so-called in the vicinity of the zero temperature, the so-called Bloch law. So with all this knowledge, we fit our data, and I think this calculated according to this nice formulas. Again, I wish to stress that we have made a very strong assumption that these two subsystems in our metamaterials are independent of each other. I guess we have quite reasonable agreement.
Can you extract defect concentration from this magnetization feed?
It affects only the amplitude of the effect, but here I plot the resonance. We assume that all the defects are independent. They're indeed independent from the measurements. They don't interact with each other.
Yeah.
So it affects only the amplitude, which I don't plot here. Now, I wish to conclude that anomalous M line is related to nanodefects or planar defects. And you may ask why the amplitude of the ferromagnetic resonance comparable to that of the antiferromagnetic resonance, because the number of the defects is tiny. It's about 1 to 3%. But in fact, the intensity of the electron spin resonance is enhanced by magnetic field. Well, by number of reasons, ferromagnetic resonance is strong. This is the very simple argument. There are a number of reasons why it is strong. And I conclude that the two-phase model fits the spin resonance data. You cannot say this is a ferromagnetic or antiferromagnetic because they're both in the same bottle that you have two effects. And more or less it's consistent when you use adjustable parameter that is consistent with magnetization measurement for the D field. So we think that this puzzle is solved. And I wish to finish at this point and thank you for your patience and my colleagues for collaboration. There you see there are a number of people from my laboratory in Xi'an, from the Landau Institute, from Yekaterinburg from Kurchatov Institute, from Novosibirsk, my former student from Dresden, and from Kazan, and from MIPT, Igor Stolarov and Igor Golovchansky. Thank you.
Thank you. Thank you very much. We have time for questions. Maybe let us first ask the online audience. Dear colleagues, do you have any questions? Then unmute yourself and ask. No one. So then, yes, sorry, please.
Thank you very much for such a great overview of such rich system. The question is that at the beginning of your talk, you mentioned about interplay of speculativity and ferromagnetism in this system. And taking into account the quasi two-dimensional nature, it should be pronounced fluctuations, for example, in excess conductivity, in meaning Varlamov fluctuoscopy of superconductors. As in the Fermi surface there are light electrons, it should be nucleation superconductivity two-dimensional, and it should be obviously in fluctuation of resistivity measurements, and at the beginning of superconductor transition, one can see the two-dimensional nucleations, like in magnetic wire. Yes, like
Okay. The answer is very simple. That first of all, I was presented here. The effects I present are robust. And you are talking about a very tiny effects and fluctuation. The second is that this the materials is not two-dimensional, it's quasi two-dimensional. There are quite strong coupling between the layers. I don't think that the fluctuations are strong, but it may be subject of interest.
What is the isotropy of coherence length, or HC2?
I can say the coherence length.
Or HC2?
This is, I cannot say, but anisotropy of the resistivity, DC resistivity is 200, is 100. 100. It's quite like two-dimensional.
It's pretty large still. It's pretty large. Because of that, you probably could see some effects.
But HC1, you see that to measure HC1, you have to make spherical sense.
HC2. HC2. Just about HC2. So it's just a shift of the resistivity transitions.
No, this is not done.
Yes, Vladimir.
About the last part, whether you measured width of resonance. So I saw that they are
Yes, we
different
did.
in width.
We did.
And why it is that?
We did measure, but I didn't present here. So there are some. It is affected by fluctuation, but spin fluctuation, the width increases as you go to the transition. And from the high temperature side.
For two lines. So
Yes.
antiferromagnetic is narrow with respect to ferromagnetism.
Maybe I have here some pictures.
In previous. Yeah, but here in this.
No,
Yeah.
no, unfortunately, I don't here. But we did measurements. I didn't notice there are any puzzles because you start from the high temperature side and paramagnetic state. Paramagnetic resonance line, the width, the resonance width increases towards to the transition point. When there are no large changes below near temperature.
Yes, good.
Since TC is larger than TM in the Euro arsenide, does this mean that you can only observe the superconductivity between these two temperatures? Since if the temperature is below TM, then the superconductivity will be suppressed by the magnetic order.
Can you repeat it again?
I mean, the TC, the critical temperature for the superconductivity, is larger than the neo temperature in the EU arsenide. So does this mean that you can only observe the superconductivity between these two temperatures? since if the temperature goes below Tm, so which is
Why
near,
magnetic volume doesn't suppress? The superconductivity, that was the question, or?
suppressed by the magnetic order.
No, it doesn't.
The question is, why the superconductivity is not suppressed? The magnetic order,
No,
is what you're asking?
I mean, so
Yes, exactly.
Why is that suppressed?
The electron wavelengths in the normal state is huge, it's much larger than the interlayer distance and inter-European atom distance, and also the Kuiper pair, the superconducting length is also very large in this material. And this is number one question. The number two question, so it on this wavelengths, it average of the magnetization and don't feel much the variation of the magnetization. And there, maybe this is the reason why the amplitude of the order parameter doesn't feel the magnetic order.
The spherical exchange field is much weaker because your Curie or Néel temperature is below the TC, and so superconducting ordering is stronger. Because of that, this weak
Because of this,
ferromagnetic ordering, it cannot suppress, cannot feel superconductivity.
the way I can,
so even below the new temperature.
Even below, because in opposite, if you have Néel temperature much stronger, much larger than superconducting critical temperature, then of course you're right. But this is not the case here.
then we deal with the p-type, triple superconductivity,
So if it is like a p-type superconductor,
Yeah.
so does this mean that it's
that's a different story.
applicant for the topological superconductor?
They can make that remark. Means that they can say that this material is not van der Waals. It's like layered, but not van der Waals. That's why it cannot be determinate like a layered structure as usual. It's why it's more volume effect of the superconductivity.
The bonding is affected by
Yes.
thin and arsenide layers. You're right.
Yes, you mentioned possible p-type. Yeah? Is it experimentally confused with these materials?
No, this is very tight for sure. It's very tight for sure. As of all other iron arsenides, it is best type. Sometimes we see some anisotropy of the order parameter, but weak anisotropy, this is S type. S type S plus minus.
It's possible.
It's believed to be S plus minus. Which
If no more questions, it's our traditional, souvenir of Abrikosov Center that I have a pleasure to
I see.
offer you. Thank you. Very nice again. So the next seminar will be
12 for November.
yes, and
Timur.
Timur is giving a talk. Okay, great. I think no, I don't have seminars today. It's 17. 17 will be about new material. It's about progress. Коллеги, прошу кофе, чай.
Короче, я пошел. Подожди, сейчас мы закончим.